Page 678, second half of section 9.7, probability. All right, we start off on the top of page 678 with a bold print term. It says two events A and B from the same sample space are mutually exclusive if A and B have no outcomes in common. All right, so if we're talking about two things from the same sample space, maybe we're talking about the sample space that we get from rolling a die, that it could land 1, 2, 3, 4, 5, 6. So if we chose two things from that same sample space, like rolling a 4 and rolling a 6, those are mutually exclusive events, meaning that they can't both occur at the same time. You could say your coin landing heads or it landing tails. Both of those can't occur at the same time. So mutually exclusive events have no outcomes in common. So you could think of mutually exclusive events, either you are a junior or you're a senior, but you're not both. Those are mutually exclusive. They can't both occur at the same time. They don't have the same outcome. And so when we approach the idea of something being mutually exclusive from a Christian worldview, what I think of is the idea that either you are a Christian or you're not a Christian. Those are mutually exclusive events. And when we're talking about mutually exclusive, they have no outcomes in common. If John 14:6 says, I am the way, the truth, and the life, no man comes to the Father except by me. And that's Jesus speaking, where he's saying, this is pretty cut and dry. This isn't what I believe or what your pastor believes or this is what the Bible says. This is what Jesus said himself. I am the way, the truth, and the life. There's no other way to get to God except through me. So you either have to accept me as your Lord and Savior and let me pay your penalty to get you into heaven, or you can choose to reject me and I'll give you what you want. I will give you an eternity completely separated from me in hell. So the outcome of being a Christian or not being a Christian, absolutely no outcome in common. Those are mutually exclusive events. And there's no cut and dry there of there's any way that I can do it on my own. It's not a gray area there in the middle of, well, hey, maybe if I do enough good stuff and it outweighs my bad stuff, or maybe I'm a good enough person, or, but just by default, everybody goes to heaven unless they do something really, really bad. That's not what that verse says. Jesus says, I am the only way. It's only through me that you're going to get to heaven. So mutually exclusive events, definitely no outcome in common. All right, then they give me a probability formula there on the top of 678, and that is the probability of the union of two events. And when we see union, that's one of those symbols that we learned in geometry, kind of looks like a U. And it basically means to unite two things. We've written some of our answers that way in our interval notation. And so when we talk about the probability of A or B, we're going to write it with that union symbol. And the formula that they give me there in the textbook is the probability of A plus the probability of B minus the probability of A. And this symbol that you see here is intersection. So minus the probability of A intersected with B. Now, an intersection in geometry is just like an intersection of two streets. It's just where they overlap. So when we're thinking about this in terms of probability, there are some things that are mutually exclusive that are never going to intersect. A red card and a black card are not going to intersect. They're not going to overlap. But a red card and a heart are going to have an intersection. They are going to overlap. So, for example number 7, it says one card is selected from a standard deck of 52 playing cards. What's the probability that the card is either a heart or a face card? So as soon as we see that word or, we're going to use our union formula. And here's what that union formula says. Find the probability of A plus the probability of B, and then subtract the probability of A intersected with B. So we're going to say, okay, if I want to find the probability of a heart or a face card, that'll be the probability of the heart plus the probability of the face card minus anywhere that a heart and a face card would intersect. All right, so let's think about our denominator. How many do I have to choose from with a deck of cards? 52, right. So my denominator all the way through here is going to be 52. Out of those 52 cards, how many were hearts? 13 hearts, right. Out of those 52 cards, how many are face cards? Now remember we said that Jack, Kings, and Queens are face cards, right? And that there would be one of those in each of the suits. So there would be 3 face cards that are hearts, 3 face cards that are diamonds, 3 that are spades, and 3 that are clubs. So we're going to end up with how many face cards? 12, right. And then we want to subtract off anywhere that I have hearts and face cards intersecting. Do you have any hearts that are also face cards? Yeah, there are 3 of them, right? And so I would just subtract that intersection off. Now think about this formula for just a second and what just happened here. When we counted the 13 hearts, did we count the 3 face cards that are hearts? Yeah. And when we counted the 12 face cards, did we count the 3 face cards that are hearts? Yeah, so we accidentally counted those 3 cards twice. That's okay, our formula's got us covered. Because our formula says, hey, let's subtract off anywhere that they overlap because you're going to have counted them in both of the groups. So we'll subtract it back off to make sure that you don't have duplication. That's what my formula's doing for me, okay? So notice that typically we're going to reduce our probability and give it in lowest terms, but I did not simplify 13/52 down to 1/4. Because when you're going to add and subtract, you need a common denominator, right? So wait until the very end, and then you can simplify your fraction. So we could go through and say 13 plus 12 minus 3 gives us 22. And then 22 over 52 would simplify down to 11 over 26. All right, look at the next one. On page 679, they give me a table. And it says the personnel department of a company has compiled data on employees' numbers of years of service, and the results are shown in the table. If an employee is chosen at random, what's the probability that the employee has 9 or fewer years of service? All right, so if we want the probability of 9 or fewer, 9 or less, if you look at that table, what falls into that category, they have one interval from 0 to 4, and they have another interval from 5 to 9, and then from there it goes 10 to 14, 15 to 19. So if we're saying 9 or less, it's just those first 2 intervals in our table, right? 0 to 4 or 5 to 9. Something else about this table that I want to make sure you understand, if I've been at the company for 8 years, I'm going to be listed in the 5 to 8 category only. I'm not going to be listed in the 0 to 4 and the 5 to 8. So the way that this table is being read, these are mutually exclusive items. I've either worked for the company for 3 years or I've worked for the company for 8 years. So it's one or the other. It's just my total years of service that we're putting in our table here. Okay? So when they say find the probability of 9 or less, on that table, that could have been the 0 to 4 interval, or it could have been the 5 to 9 interval that would fall into that category. So again, if we have or, we're going to say the probability of 0 to 4 plus the probability of 5 to 9 minus the intersection of 0 to 4 and 5 to 9. All right, so let's think about our denominator. Our denominator is going to be the total number that we have to choose from, right? The total number of employees. They were not kind enough to tell me what that is. So I have the joy of that column that says number of employees. I have the joy of adding that. So I need to go through and do 157 plus 89 plus 74 plus 63 plus, all the way on down, right? So when I add all of those up, I can throw them in my calculator. When I add all those up, I'm going to have 529 employees. So that's going to be my denominator. Total number we have to choose from. All right, so out of the 529 employees, if I look at the table, how many of them have been there 0 to 4 years? 157, perfect. And how many of them have been there 5 to 9? 89, exactly. So what would the intersection of 0 to 4 and 5 to 9b? Well, it would be 0, right? Because those are mutually exclusive events. They can't both happen at the same time. Either I've worked there for 3 years or I've worked there for 8 years. It's my total years of service. So that last piece, that intersection, is just going to be 0, and it's going to drop out. So again, we would want to combine this while we had a common denominator and then simplify our final fraction if it would simplify. Now, if you're comparing the formula that I gave you for the probability of an OR statement with what they have in the book, you'll see it's different. Because in the textbook, they give you 2 different formulas for the probability of one thing or another. And they tell you, if your 2 events are mutually exclusive, you need to use this formula. But if your 2 events are not mutually exclusive, then you need to use this formula. I would propose to you that you don't really have to memorize 2 different formulas under 2 different circumstances. Because the only difference in their formula is they say, if your events are mutually exclusive, instead of using this formula right here, if your events are mutually exclusive, then drop this piece off. Well, if my events are mutually exclusive, then what's their intersection going to be? It's not going to be there, right? It's going to be 0, right? That piece will drop off itself. So rather than my having to memorize 2 different formulas under 2 different situations, and I can just use that same one formula every time, and if my events are mutually exclusive, I'll get a 0 right there, and that piece of the formula will drop off on its own, and that'll just make the whole process a little simpler. All right? Then over on page 680, they talk to us about the probability of one thing and another thing. And so if we have the probability of A and B, that'll be the probability of A times the probability of B. Probability of A times the probability of B. So look at example number 9. Example number 9 says a random number generator on a computer selects 3 integers from 1 to 20. What's the probability that all 3 numbers are less than or equal to 5? So we can say, okay, if all 3 numbers have to be less than or equal to 5, that means the first one is less than or equal to 5, and the second one is, and the third one is, right? They didn't write it that way. I have to interpret it that way. So anytime they tell me both of these have to be this way, or all 5 of these have to be this way, or all 3 of these have to be this way, that's an and statement where I'm saying, okay, the first one and the second one and the third one and however many there are all have to follow suit. So for this one, we could say, okay, the first one has to be less than or equal to 5, and the second one has to be less than or equal to 5, and the third one. So according to our formula up here, we're going to find the probability of the first one times the probability of the second one, and just keep going for as many of them as we have. That feels kind of familiar, right? Does that feel a little bit like fundamental counting principle? Like if the first thing can be done in this many ways, and the second thing can be done in this many ways, and the third thing, I just multiply them? Very similar idea. So we could go through and say, let's find the probability that the first one is less than or equal to 5, second one is less than or equal to 5, third one is less than or equal to 5, and we'll multiply those. Okay? So it said that the computer could generate numbers from 1 to 20. So we obviously have 20 to choose from. And it says, what's the probability the number is less than or equal to 5? So how many of them are less than or equal to 5? 5, right. So we would have a probability of 5 out of 20. For the first one, 5 out of 20. For the second one, 5 out of 20. For the third one. Do you need a common denominator to multiply fractions? No. So unless you just enjoy multiplying big, huge, large numbers and then trying to reduce them down for 3 minutes afterwards, it'd be much better if we went through and simplified each of those fractions first, reduce them down before we multiply. So I would simplify 5 over 20 to be 1/4, and then I can just do 1/4 times 1/4 times 1/4. I get to the end, it's already in its most simplified terms. Now, there on page 680, they give me a bold print term, and the bold print term is independent. It says 2 events are independent if the occurrence of one has no effect on the occurrence of the other. That would also lead us to think then that there must be dependent events where the occurrence of one would depend on the other. And we actually see both of those in our homework, even though they don't define dependent events here. So let me kind of explain to you what that would look like. We've seen this before. If you remember, back when we were doing fundamental counting principle, we had this example where we have a box and the pieces of paper are numbered from 1 to 8, and we're going to pull out a piece of paper and then put it back in and pull out a piece of paper. And then the example right behind that, it said we're going to pull out a piece of paper and not put it back in and pull out another piece of paper. We talked about that was with replacement and without replacement, and it would change our counts. It's the exact same idea with probability. Let's think of it as a deck of cards, okay? If I'm talking about a deck of cards, and I say I'm going to pull 2 cards out of a deck of cards, all right? If I say I'm going to pull out a card, then the total number that I have to choose from is 52. So whatever it is they ask me to find, hearts or red cards or face cards or whatever, we're just considering the denominator right now, okay? So the first card they tell me to draw, I'm drawing out of the whole deck, my denominator would be 52. If they say put that card back in the deck before you draw the next one, then the second card that I draw would still be at a 52, right? Those would be completely independent events. The fact that I put the card back in, that it was with replacement, would mean that when I go to pull that second card out, that probability is completely independent. It's not affected by anything else. But if they said pull 2 cards out of the deck, pull the first one out and leave it laying there on your desk, and then pull the second card out, we would call that without replacement from when we saw this before, then that means that the denominator of my first probability would be 52, but the denominator of my second probability would be 51, right? If one of the cards is still laying on my desk, I only have 51 left in my deck to choose from. And so we see that in the homework. Sometimes they do it with cards, sometimes they do it with marbles, sometimes they do it with pieces of paper. But they'll say with replacement or without replacement. Or they'll say I put the card back in before I pulled the next card out, or I pulled 2 cards out at the same time. And so you can see how sometimes those events will depend on each other and they'll alter the probability. I'm still going to take the probability of the first one times the probability of the second one. It's just that sometimes when I do the probability of the second one, it'll be affected by that first one if they're dependent events. Okay, then over on page 681, example 10 before we move to 681. Example 10 says, in 1997, 58% of the population of the United States were 30 years old or older. Suppose that in a survey, 10 people were chosen at random from the population. What's the probability that all 10 were 30 years old or older? All right, all 10 were 30 or older. That means the first one is, and the second one is, and the third one is, and the fourth one is. It doesn't say and, but when they talk about several of these being something, then we need to understand it that way. So we could say, okay, the probability of the first one is greater than or equal to 30, and the second, and the third, and the fourth, all the way up to the 10th. So according to our and formula up here, we're going to multiply each of those. So first one times second one times third one times fourth one, all the way up to the 10th one. All right, so let's figure out our probability. If it said 58% of the population is 30 years old or older, how can I write that for probability? 58%. Probability is always a number between 0 and 1, right? So how do I write 58% between 0 and 1? 58 over 100 or 0.58, right. Both of those are correct. So you could write 58% as a fraction, 58 over 100, or you could write it as a decimal, 0.58, whichever you prefer. So the probability of the first one, and the second one, and the third one, and the fourth one, all the way to the 10th one, that would be the same. So how could I write that? To the 10th, perfect. So whether you used a fraction or a decimal, you could raise it to the 10th, you could throw that into your calculator and get your probability. All right, then on the top of 681, they talk to us about the complement of an event. And it says the complement of an event is the collection of all outcomes in the sample space that are not in A. And the way that we're going to write a complement is we're going to write it with like a little prime mark after it. A prime, that's the complement of A. And the way that I can find the probability of the complement is to do 1 minus the probability of the event. So one more time, it says the complement is the collection of all outcomes in the sample space that are not in A. So you almost can like throw out the word not in there. For instance, if we said the probability of us winning is 0.3. If A, my event A, is winning, then its complement would be, just throw the word not in there, its complement would be not winning. So if the event A is winning, then the complement of A is not winning. If the probability of A is 0.3, by common sense, we would say, okay, well, if, I've got 0.3 or 30% chance of winning, then I've got 0.7 or 70% chance of not winning, right? Well, we could get that from that formula as well, because the formula says if you want the probability of the complement, it's just 1 minus the probability of the event. So that's logical to us. It makes sense when we see that, where they're getting that from. Go back to number 17 on the homework from last night. For number 17 on the homework, it said, find the probability in the experiment of tossing a 6-sided die twice, and the probability they wanted us to find was that the sum was less than 12. All right? So if I'm trying to find the probability that the sum is less than 12, well, sums less than 12 would be 11, 10, 9, 8, so all the way down to 2. I don't necessarily want to sit there and list all of those out. Okay, what are all the ways I could get a sum of 11? All the ways I could get a sum of 10, 9. I start to look at that and go, it'd be a whole lot easier to think about what would be the ways that I could get a sum that's not less than 11. And so some of you, when I was looking at your homework, that's exactly how you did that problem. You went through and you said, okay, all I need to do is figure out the probability of a sum that is not less than 11. There's only one of them that's not less than 11. It's 12. There's only one way to get that. So if there are 36 total possibilities, because the first one lands 6 ways and the second one lands 6 ways, we multiply that, fundamental counting principle. We've done that several times already in our examples. And so if there's only one way that I can get a sum of 36, then the other 35 must be ways to get a sum less than 12. So a lot of you on your homework had done it that way, where you had just kind of used common sense and said, if there's only one way to get a sum that is not less than 12, there must be 35 ways to get a sum that is less than 12. You were actually using the definition of a complement and didn't even know it, because it's very logical. Where I could go through and, according to the formula, if I want to find the probability of the sum being less than 12, then I could do 1 minus the complement of that. And the complement of that is the sum is not less than 12. I just throw the word not in there. If it's not less than 12, then my only other option is greater than or equal to 12. Well, if you're rolling 2 die that have 6s on them, then you can't have anything higher than 12. So I could say 1 minus the probability that the sum is 12. There's only one way to get a sum of 12, so I could get that 35 over 36 that way as well. So common sense or formula, either way you want to go, going to lead you to the right answer. All right, so here is our homework for tonight on pages 682 to 683.